Here is a matching type question on general organic chemistry. Study the items in both columns carefully. Try to work out the matching before we solve it together. Let us first understand the key concept here. Boiling point depends on intermolecular interionic forces. NCl3, ClNH2, and NH3 are molecular compounds held together by van der Waals or hydrogen bonding. NH4Cl is an ionic compound, ammonium chloride, composed of NH4 plus cations and Cl anions. Ionic compounds have extremely strong electrostatic, cation-anion interactions, giving them far higher melting and boiling points than molecular compounds. NH4Cl sublimes decomposes at 338 degrees C, far above the boiling points of the others. Therefore, NH4Cl has the highest boiling point, and the responsible force is cation-anion ionic interaction. Why others fail? NCl3, BP 71 degrees C, has only London dispersion. NH3, BP minus 33 degrees Celsius, has H bonding but is still a small molecular compound. ClNH2, BP 66 degrees C, is also molecular. B. Highest boiling point among cyclobutane, cyclopentane, methylcyclohexane. Let us first understand the key concept here. For nonpolar hydrocarbons, boiling point increases with molecular weight and surface area, London van der Waals forces. Cyclobutane, C4H8 MW is equal to 56, cyclopentane, C5H10 MW is equal to 70, methylcyclohexane, C7H14 MW is equal to 98. Methylcyclohexane has the highest molecular weight and greatest surface area, so it has the strongest London dispersion forces and thus the highest boiling point, 101 degrees C versus cyclopentane 49 degrees C versus cyclobutane 12 degrees C. The responsible force is van der Waals, London dispersion forces. C. Most soluble in water among phenol, catechol, 1,2-benzenidyl, 1,2-benzenidiol. Let us first understand the key concept here. Water solubility is governed by ability to form hydrogen bonds with water and polarity. Phenol has one OH group and can H bond with water. Catechol has two OH groups in ortho positions, both can H bond with water, and the intramolecular H bond possibility is limited compared to intermolecular H bonding with water. More OH groups generally means greater water solubility. 1,2-benzenidiol has Sh groups. Sulfur is much less electronegative than oxygen and Sh groups are much weaker H bond donors acceptors, so dithiol is much less water soluble. Catechol, 2 OH groups, is most soluble in water. The responsible force is hydrogen bonding and dipole-dipole. Why catechol phenol, 2 OH groups provide more sites for H bonding with water than one OH in phenol? Why dithiol fails? Sh is a poor H bond donor compared to OH. D. Highest solubility in benzene among pyrrole and pyrrolidine. Let us first understand the key concept here. Benzene is a nonpolar aromatic solvent. Like dissolves light. Pyrrolidine is a saturated, non-aromatic, secondary amine. It can H bond with itself, NH, and is more polar. Pyrrole is an aromatic heterocycle with a conjugated pi system. It can interact with benzene via aromatic pi stacking and dispersion interactions, making it more compatible with the aromatic benzene solvent. Additionally, pyrrole's NH lone pair is delocalized into the ring, reducing its H bonding ability compared to pyrrolidine, making pyrrole effectively less polar and more aromatic-like. Thus, pyrrole is more soluble in benzene. The responsible force is aromatic stacking, pi-pi interactions. Why pyrrolidine is less soluble in benzene? It is saturated, more polar, and prefers polar solvents. Therefore, the correct answer is A. Compound NH4Cl force cation-anion interaction, B. Compound methylcyclohexane cyclohexyl CH3 force 1 der Waals forces, C. Compound catechol benzene 1,2 diol ortho-dihydroxybenzene force H bonding, also dipole-dipole, D. Compound dihydrole with NH cyclic secondary amine 5-membered ring with 1 C is equal to C force aromatic stacking. Therefore, the correct matching is A. Matches compound NH4Cl force cation-anions interaction, B. Matches compound methylcyclohexane cyclohexyl CH3 force van der Waals forces, C. Matches compound catechol benzene 1,2 diol ortho-dihydroxybenzene force H bonding, also dipole-dipole, D. Matches compound dihydrole with NH cyclic secondary amine 5-membered ring with 1 C is equal to C force aromatic stacking.